and welcome to another day of our Lord Odin, of course, on his day, Odin's day. Now, how is everybody doing? I hope so. I hope very well, in fact. So I am going to do, as we all normally do, is tell the appropriate social media sites and other forums and stuff where to go find out where to watch. So I'm going to put that in the announcements chat as well. So the question is, what am I doing today on this wonderful day of the day of our Lord? That is, like, I don't know, Wednesday, Odin's Day. Okay, so we're going to wait till some people come on, because it is slowly getting up there. It's getting up. Rightio. Okay. So today I'm guessing I was going to work on something because the people requested it, at least. And that being getting the Odin parser, printing as well, so I get a nice little basic printing formatter, because at the moment it doesn't really format any code. It just, people want a formatter, but the problem is with formatters, they get a little complicated. So this is the question, how do you deal with it? I was thinking one idea. Another idea is we can do a more compiler development or some standard core library development, whichever is more preferable. It's up to people to decide. Because also, now that I've already got the latest release out a couple of weeks ago, or whatever it was, just whatever, I can now, this is the thing, is I can start working on the debug information for the LLVM CA API backend, which means the sooner that gets up and running and also works on other platforms as well, the sooner we can completely deprecate the old backend and then eventually get rid of it. That is the entire plan, by the way, guys. So for the next release, whenever that comes out, is getting debug information for the LLVM C backend. Then is making sure it's all working on all the new platforms. Then it's also deprecating the old backend and then removing the backend. It may not all happen in different versions, of course, but there will be in that order. Of course, other good news today is someone in the community, which is Crixano, I'm not pronouncing his name correctly because I cannot be bothered to pronounce it correctly, has got Odin compiling and working for FreeBSD, which is wonderful. Everybody, clap your hands. That's absolutely hunky-dory that we have now got FreeBSD working absolutely fine. Okay. So everything is going to be fixed completely for the new backend. I'm going to have to rework the entire calling convention system anyway, because if I'm going to be supporting loads of different APIs, which there are multiple, I need a better system that's more generic than the system I have. So the new backend system is I'm going to have to rewrite all that completely. So that's going to be fun to figure out how to do that and get it working in a way that is generic enough, but also useful enough for everything as well. So yay, so many things to do. But yeah, what else is there that we need to do, work out as well? Oh, other news for people who are listening. If you didn't, I'm going to ask you, how is the sound quality for tonight's stream going along? Because I'm trying to make sure everything sounds okay, the volume is okay, it's not too loud, etc., etc. How does it sound? Sound good? Is it too loud, too quiet? No, fine. Because the real reason I am asking is it sounds approximately twice as good as it did last time I saw the stream. That is very, very good to know. Because I bought myself a new microphone, if you didn't know. My previous microphone was, my previous audio interface was dying on me. I had it's because the other one before had serious driver issues, and then so I had to get a new one. So I got myself a new audio interface instead of the microphone. And while I was there, I thought, you know what, let's get myself a new microphone, because the microphone I had was probably 12 years old at least. Well, when I bought it 12 years ago, it was third hand when I got it. Third hand, not second hand, as in there were 2 previous owners before I got it. Yes, it was that. So it's probably 20 years old, the microphone is. Who knows? So yes, the microphone that I've got is the Rode Podcaster. Now, it's a pod mic. I was actually looking at all the other ones, and I was listening to the audio tests between the other things. There was a Rode pod mic, and the other one was what was the other one? And it wasn't that more expensive. There was another one that they were doing. What was the other microphone that they were doing? They had the pod mic, which is the one I've got now, and the other one was called Procaster. That was it. I think it was Procaster. And they weren't that different in price. I actually, when I was listening to audio test people using YouTube and stuff, I actually preferred the tonal quality to this microphone than the one that was more expensive, even though the other one's got a bigger body and should theoretically have a better sound quality because of the physics. I actually just preferred this when I was hearing people using it. So I thought, okay, I'll get this one. So I hope everybody is sounding good. It's a dynamic microphone, which is different to what I'm normally used to, which is a condenser microphone. But the thing about dynamic microphone is it doesn't pick up all the noise around me as easily, but it does mean I have to be much closer to the microphone when I'm speaking. So I'm asking, how does it sound? Hope it sounds good. And yeah, that's hopefully hunky-dory, as I keep repeating multiple times. And yeah, Rode usually make good microphones in general. I've used quite a lot of stuff. There's also the other one I was thinking about, which was about 3 times the price, I'm not doing good with the names tonight. I can actually imagine what it looks like in my head, but that's not very good when people are trying to... I'm not showing images. What is the Shure microphone? That was it. It's the Shure... Is it Shure? Is it the Shure SM... Yeah, it's SM7B, which is literally about 3 times the price, 4 times the price than the one I bought. And it is one I've actually used before when I was in radio stations. It was like pretty much the standard everyone used. Because it is a really good microphone, especially for the price. And if you want to go better, you're spending 10 times the price. And it's really not that much better compared to that, yeah. But yeah, the Shure SM7 bikes are like the ones for vocal microphones, especially for radio stations as such. So if you are going full out, you'll go for them. But the one I've got now is this one, isn't it? It's got quite a nice body on it. It's quite good. So at least it sounds good to people. Because the other reason why I've been doing this... Yeah, and so I've also put a bit of EQ on here as well to counteract my voice. So I actually... I increased some of the bass and a bit of the trebles, reducing the... I was doing some EQ. I know how to do EQ, let's put it that way. Hopefully it sounds okay. What else did I do to the vocal quality of the microphone? Oh yeah, I put a noise gate on and just compression as well. Compression is mighty key into getting it sounding nice and crisp. Because then it, again, as compression does, it compresses the audio. Not compresses like digital compression, you know what I mean? It's the same thing. And then, what else is there? Yeah. So the other thing I was actually talking about is... what's the word? Oh yeah, so the main reason I actually got the microphone, to let people know, is I was considering starting my own podcast. And the reason as to why I was starting my own podcast is because I've been wanting to write loads of articles, and I am not at all a very good writer, and it takes me forever to write everything. So instead of writing, I'm actually much easier than speaking it out loud and getting my ideas out like that, which is a lot easier to do most of the time. And when I've got these ideas, again, if I speak them out loud, talk to people and trying to get them, and try and pretend if as I'm teaching them, I can better understand the ideas that I'm trying to express. Even if I'm wrong about those ideas, trying teaching them means you can actually test that you actually understand them better. So hopefully that is a word that, yep, it makes sense. So, I have got a few ideas, at least for the next podcasts, that I want to do. So I need to start getting them recorded, in my DAW, and then edit them, and then upload them to wherever I host them. I have no idea where the best place to host them yet is, but I'll figure it out. Hey, it's baby steps. It's baby steps, as they say. So should we, as everybody is suggesting, which they aren't, by the way, I'm just making that up, get on with the show and start programming? Shall we? Well, you can now... Wait a minute, is it working? We can now see the programming background, and hopefully we can get on with the show. Okay, so first off, I am just compiling the Odin compiler to be in build mode, because I wanted to be there. And what was I doing here in test? Oh yeah, I was doing crap here, wasn't I? That was all. I had a new intrinsic, which was type has field. That was all I was doing. Very, very basic thing. Nothing out of the ordinary. Now, let's get rid of that. So one thing I was working on was fixing the Odin parser that's in this core library. Yes, so thank you for the question. So the question was, oh, by the way, how is it now to work professionally with Odin? And that is correct. I am now working as my day job, programming in Odin every day. That doesn't mean I am programming the compiler every day, but I'm actually programming the language. It's gone to that point where it is kind of surreal, is the best way of putting it. Surreal in the fact that I wasn't ever really... I made this a bit bigger anyway. I never thought this would happen. I know that sounds daft. That was kind of the point I made it for myself, but it just happens. It's bizarre. And at least other people are using it and making tools out of it, which they can make money off. It is surreal. This is happening. It's quite nice to know. Thank you for the question anyway. Yeah, that is wonderful. But I'll be right back after these important messages from Static Noise. And we're back. I hope Static Noise was very good. I hope he was very kind to you and he wasn't too distracting with the noise, of course. But hey ho, you never know. So, right, what I was doing here is I wanted to fix some of the bugs that I still had in the parser, and some of them were with... someone said, yes, thank you for correcting them, and I'm fixing them as I go along. So, let's go. This is just my test. Okay, so that is me parsing it correctly, and it's parsing that demo file. Okay. Yeah, shall we put him back on? Let's get Static Noise back on. Get him back onto the show, guys. Ready? And here we go. Actually, no, sorry, that's just enough. I'm sorry, I can't let him keep talking. He's absolutely insane. That Bill Chab, no, he's not insane, but yeah, that static noise, don't like the man at all. No, I don't need to go to an insane asylum, but... Okay, so someone's saying thank you for working on the core parser, and this is on... We should probably just show it so everybody can see the thing. This is one of the issues that I'm showing. And it says, since some of the bugs got fixed yesterday, I checked all the issues again. All of the old ones except one seems to be fixed. Ooh. I was able to make them work again and generate the correct code. The one that doesn't seem to work is break, continue, and fall through. So they are the branch statements. Using the results in the following branch, notice the token kind. So it says branch statement. And then it says invalid. Interesting. That is actually very interesting. It says, also found a new one, but this isn't really a bug. It's just our oversight most likely. There is no indication if a nested struct has using. Ah, that's very true. I need to actually do this. I am accidentally bumping the microphone stand. Yes, that is absolutely correct. You're not just hearing things. I'm hitting it, and it's making that creaking noise, which is, again, the microphone stand itself is probably a decade old at this point. Yes, I've had it that long. It works. It's full of duct tape, but it works. And probably needs a bit of grease. But yeah. So don't worry, you're not hearing things yet. We haven't got to that point of the night. I'm drinking the hard stuff at the moment, which is lemonade. Diet lemonade. Oh. Who would have known? Who would have known? So, let's think out on how do we solve the bug that's here. Because it says the token kind is invalid, and by the looks of it, it's not invalid, it's just not being set. Which is simple enough. We just need to go into the parser, .Odin, and then we look for the branch statement here. And look, it is invalid, because guess what I don't do? Isn't that exactly what the problem was? That I just don't set it up? And then it says, yes, so what we need to do is AST branch statement, and it says identifier. I'm going to do that, and now it works correctly. So let's first off just say that we fixed it. And I know it works because I know what the problem was, and it's, oops. There we go. I know what the problem was there as well. So we're going to commit. We are going to say AST branch node parsing in Odin parser. There we go. So we're committing and pushing that, and off she goes into the heavens, which is now called the cloud. I know, it's more modern technology, and they got to get the terminology for all those folk. Of course. Right, and then the other thing was using, which is an oversight, of course. We want to look for the struct type. Yes, I am not insane. Don't worry about that yet. Yeah, we're going to pass the field list, and yes, you are probably correct that field list, we've now got a list of fields, and they should also have the field flags, especially they should state if they have struct flags, if they have using in there. Okay, so we have the flags, and they do get assigned to the field. By the looks of it. So if that's not the case, then Interesting. Where does the set flags get? They get past there, don't they? There's the flags. And then they get... Well, I don't see any problem. Also, I don't technically need to do that. I'm just going to do that to simplify it like mad, what I just did. Wow, magic. I am a genius, me. I love the implicit selector syntax because it does that. It cleans everything up. How does everybody know that? Oof, who knows? Yeah, magic. Yeah, I know, right? But the thing is, what was the bug that you were saying is this. So we are passing the demo file like so, and it should be, this is one of those things where, do I have any form of using in a struct? I do, I have it in the frog struct. But sorry, someone's got a chat, okay. You probably overlooked the flags, I don't know. It looks like it's correct without even checking, but it looks correct. That doesn't mean it is correct, but it is looking correct. Another one is, another issue we talked about was, there was a compiler crash. Oh, so this may have actually been fixed. It's an old bug, but thank you for BT Telly, whatever you want to call him. It might have been nested structure, nested type. There's no such thing as a nested type node. So let's look at the new pull requests, because there was one. Thank you. Got a new one that's open to our. Aha! No, I know exactly what that bug is. Thank you so much. That is actually... that is exactly what I wanted. Isn't this lovely? I want to say thank you for BT Telly, or whatever you want to call yourself. I have no idea how to pronounce that name. I apologise. But thank you for fixing some of the bugs lately. It's been an absolute pleasure. Seriously, it's been getting it... It's helpful when people do that. It's nothing stronger than lemonade. Don't worry, I am this insane normally as well. I can go on to the stronger stuff, if needed be. It may actually mellow me out a bit, so... So thank you, yeah. I wanted to go into the PR request, because there's one thing, again, similar... Wait, is this a draft? Yeah, it's still draft, isn't it? Yeah. Yeah, because I was saying, Crixano, I know that's not how you pronounce your name. It's going to take me a while to figure it out. Yeah, you got... what was it? You got FreeBSD working... the other day, which is amazing, and you're trying to get ARM64 working as well. Now that's going to be a bit harder because, again, I haven't really supported generic APIs, and I really need to somehow. So thank you for that. There's also this thing again, I'm going to call you BT now for this easiest clear. There's this new pull request. I'll make it bigger so people can see this on the stream. Now I'm not actually sure. It's one of those things where it is, again, it's very simple to add. It's been implemented. He's implemented it, however, very simply. But I'm not sure of the benefit of it. So the argument is here, as Tetralux is showing, is that you can have the same signature type, but the only thing that differs is the actual argument name. So the argument names. So you could, as long as you call by the argument names, you can differentiate between the procedures, which is quite interesting when they're in the procedure group as well. I'm not sure if this is a good idea or not, because I'm trying to figure the practical use. Now, he came up with one of them here, which is this case, when I'm saying, no, distinct typing is a much better use case for that. This one is actually a very interesting use case. That it's one, again, is still, is this better done with distinct types than the distinct names? And it is a really good question to ask, and I'm going to ask other people. I don't know if this feels correct. It's such a minor thing, obviously, to add, because I think even he changed 3 files. Yeah. One of them was just to show it in the demo. One of them was just to add a thing. And then literally, that is the entire code to get it to work, to differentiate by the different parameters in there. And that's what it's going. That's where it's like, okay, clearly that's effectively, we'll say, we can't call it 3 lines. Let's call that 1, 2, 3, 4 lines. 4 lines then, really, of code. Because you've got the 2 declarations and really 2 logical lines. So you've got 4, 5 lines of code, yeah. 4 or 5 lines of code, however you count it. And it is one of those where, look, again, I do prefer the distinct typing, and this is actually a duration. Both of these are. They're just constants, but the thing makes more sense and you don't have to have overloading. This is another good example as well, especially when I've got the new container type, which is for my ring type that I added. But you can have a ring link before and after, and they can't be confused because you have to explicitly call them by the elements. Now, again, don't know if that's a good idea or not. So if people honestly do have good ideas about this, please tell me. It is another thing. What was the other thing? Yeah, so this, I should say, should probably work. Shall we get on to the thing I actually wanted to work on? Which was, yeah, seeing if I can get a printer for this AST, because this pass, because I didn't actually implement one, I don't think. It would probably need to be another package, because it's technically, once you've passed it, you've got the AST, and then you need to convert it into... Oh, what's the changes I did to the commit changes? So show changes. Oh yeah, so I'm just do that, call that minor stylize, a minor style change in parser.odin. So that was the, I was like, what did I change? Oh yeah, that's what I changed. It was just a minor change in the styling. Done. So yeah, the one thing... what was I thinking of? Yeah, I was saying I haven't done this because the thing is, this is actually how I would write the Odin compiler. So effectively, this is going to be bizarre, so I'll explain. There will be the Odin stuff here, so the AST parser tokenizer, but then there'll be an actual compiler which will have its own implementation of everything else, and that'll be effectively one giant package, I think. Maybe it's one package for the front end, and then you got a package for the back end. But the reason why I'm going to have to do that is because I wanted these libraries to be separate, the tokenizer, the parser, and the AST, because I wanted people to be able to use them separately. For the plain reason, they are functionally separate. If that makes any sense. So even though they are, you'd probably use them all together. There are many people, like for instance, I know some people who use the tokenizer because it's really good for generic tokenizing. Even in like C-like languages, it's very useful. And you can do stuff like that. There's quite a few things in that as well. For instance, the AST. I was going to... is that me making a writer for the AST? Yeah, I never finished it. And yeah, I think the writer should be in here as well, because it is in the AST thing. But yeah, it's how you want to write the thing for it. But yeah, there's quite a lot of things here, so we could probably go through. Like so. Then with this, okay, you've got a few selector selections, you've got an index selection, dereference expression. Oh, there's a hell of a lot here, isn't there? Obviously. It's also the problem with stylizing stuff, because you've got to make sure. Let's just keep it simple. Again, if people have any questions, please do. So don't worry, this is where your question is slowing down the compiler. Actually, it's not that more slowing down if you're doing by parameter name. Actually, effectively the same speed. Because you still have to go through, check every single one, so it's still in linear time. It's not, you can't really... Well, it's not true, that's not in linear time. You're checking through all of them first. then you effectively check to see, okay, which of these can take this number of parameters. You cut them out. So it's a very simple checking list to cut out which is possible. And then you also have to do a ranking. So actually, I might explain actually how this the procedure group's logic works for people on the stream if they would like to know. Proc groups. So proc group entities. That's probably not the one people want to see. Oh, let me see. What is the best proc group entities? So I'm trying to figure out what is the best logic for this. Okay, it's this case here. So there's not a single case for the proc groups. So that means we have to differentiate between them all, okay? Yeah, because if you do this, there's not as actually multiple it could be. So the differentiating is actually, I think the rules are very, very simple. You go through the proc groups, make sure it's the proc type, so that's just a sanity check. You go through the variables, You make sure that the parameters, that's fine, that's not actually what I wanted, it's... Is this it? Yes, this is the call arguments thing. Okay, so it's... Yeah, it's in two different places. Oh, it's confusing. So the ABI actually has nothing to do with the actual front-end stuff. So the ABI is fundamentally a back-end thing. And even though I do it technically in the front-end, it's not really... It's where I'm like, look, I need to fix it and allow it so you can theoretically have multiple ABIs even on the same platform, because it's just not programmed correctly at the moment. And it's... let's put it this way, there are multiple ABIs even for the same architecture. Okay, so the question is, no, I am not writing a self-hosted compiler. I was just fixing up the parser for the Odin. There is a parser in the core library of Odin itself, which is Odin, the programming language, if you want to know. You can get it at this webpage here, which is odinlang.org. And you can get it, as you can see here, absolutely wonderful, no problems whatsoever. And I recommend if people are going to use it, get the nightly builds as well. So you can go into downloads and get the nightly builds. It's very, very useful. Yes, the Windows one is bigger than the others. The reason for that is because it includes other binaries which are required, which are not required in the binaries because you can just install LLVM on the Mac and Linux. There's also now going to be we got free BSD support thanks to someone in the community, and that won't be the night build yet, but you can get it working on FreeBSD. But no, I'm not doing any self-hosting. The original plan for self-hosting is when Odin, the version 1.0 is released, that will mean the compiler is still written in C++, but it's Odin adheres to a specification that I wrote, and it makes sure the compiler adheres to it. And then for version 1.1, the entire compiler will be written in Odin. Okay, so then you're doing the bootstrapping stage there when the language is adhering to a specification, and that's the most important thing, correct. Because that's the one thing about many people who do bootstrapping very early on. They do it because, oh, it's really fun to do, and yada, yada, yada. And yeah, it becomes masturbatory pleasure. That is all it is. And I've said this numerous times before in those frames, but yes, that is masturbatory pleasure, and it's not necessarily what you want from the language. And then when you've got bootstrapping, you actually have issues because then you have to do real nasty tricks to get the actual bootstrapping out. So it's not worth it, in my opinion, no matter how useful it can be to get it. Okay, thank you. You said that you've tested it and then it still doesn't work with using. Okay, we can probably fix that in a minute. But yeah, I was trying to explain the procedural stuff. Anyway, so the proc groups things is effectively what you have is a score, depending on what arguments you've given. And what actually, it's a little bit simple. It's actually a bit more complicated than that because it's not that simple. The code is probably not the best thing. Is if I can get myself my tablet out, my graphics tablet, I need to get myself a new one because this one is okay. It's fine. It's again showing its age. Having to plug it in, that's it. And there we go. So now we're going to get Milton up. That's not Milton, that's Milton. Oh yeah, I was explaining CSP last time, wasn't I? Haha, great. Okay, so just testing this works. So what I was explaining with the proc group stuff, so let's say you have proc groups, yeah? And this proc group, let's say you've got function A and procedure B or whatever, procedure A and B, fine. So if you give it a set of arguments, it's very simple. So if we have, let's say I'm going to call this F, like that, yeah? This is your procedure group, or explicit procedure overloading is another way of saying it. Let's say we called F, and we put the procedure of 1 in. So the way it works through the rules is that we are going to look through, this is actually, the rules are pretty simple, but they make intuitive sense, but actually no, I was going to phrase that. They make intuitive sense, but they're not actually simple rules. There's quite a lot of them. So I'll explain them all one by one first. So the first thing is you look through all of the procedure. You look to see, is this calling by argument, or is it called like names or by value? So a name would be x equals 1. So it first looks to see that is the case, okay? Fine. So first off, it grabs, if whichever it's doing, it's slightly different logic. Slightly, but not much different. So if it's not in this case, what it does is it goes through every single procedure. In this case, let's just define these up. So let's say A effectively has got the signature of, say, an int, and then returns an int, yeah? So that's proc there. And then B has got the signature here of, let's say, an F32, and then returns a ball. Let's keep it, again, we're keeping it simple. It goes through here, and it evaluates this initially, and it says that this evaluation is an untyped integer at the moment. That's how it works. It's very clever in that regard. And then it goes through every single iteration, and it gives it a score to which one's a better fit. So in this case, the untyped integer fits better on the int than it does on the F32, so it will go for this. Now, if I actually wrote, let's go for the eraser, can I get off the eraser? How do I go back to a pen? I can't remember. B for brush. If I wrote this, which is now an untyped float, it will actually go to the float, because it's actually a better fit, which is the fitness score is how you're figuring it out. So that's the very simple rule, is whichever the better fit is. There is also some nice type inference stuff. For instance, if loads of the parameters are actually in the procedure group, actually the parameters in the order actually share the same type, we can use that as a type hint. So that means if these weren't, let's say, imagine these were structs, yeah? You could effectively do this, and the procedure group would actually understand. You wouldn't have to prefix it with the type in the type. You can actually figure out, as long as that argument position is the same throughout, or it can be inferred at least in that regard. Okay, so it's an inference rule, is if the target type can be known, then you can infer what the input type is. Okay, the other one is, again, it was the named arguments. So in this case, x. So it looks for any of the parameters that have x in them. If none of them have x, it knows it's not going to be any of them. Or it would at least try and find the best scoring one that it would just tell you this is wrong. Yeah, so it looks for the names first. And then and then once it found the names, it's going to associate and do the same previous rules for the named positional arguments instead. Hopefully that makes sense when you're doing the different names and such for all the wonderful things. Okay, so hopefully that makes more sense. Yeah? So that's procedure groups, and personally I find these to be a hell of a lot nicer than normal implicit overloading, like in most of C++ and stuff. And they are better than C99's generic for this particular case, because in most cases when you want generic, which is the this is C11, this is effectively how you want to treat them. because most of the time you're actually just wanting it for procedures. You don't actually want it for any of the other fancy things that you can do it for, which you're effectively, it's a switch on types. That is literally what it is. It's a switch on types, but they're constant switches. They're only varied at compile time. But it is one of those where most of the time you're just trying to do it to get operator overloading. Oh no, function overloading, not operator loading. Because you may do a generic here, I can't remember what it exactly. I'll say gin, generic. I don't even like gin. Why was I even writing it? Gin's horrible. Junipers are disgusting. They just remind me of pine oil, which is what they're from. But yeah, you know. So you can choose, I think if I can remember correctly, you say, hey, if you got a float here, you do this procedure. If you've got a double, you do this one. And it's very good for math stuff, of course, but it's only single parameter. Odin doesn't work on single parameter. Odin works on the entire parameter type signature of the procedure. So, okay. Yes, so procedure groups are pretty useful to have, and you're right, if you're saying you can make a tool to automate generic, I guess this is for foreign code. One thing I will warn about is don't overuse procedure groups. Like with normal overloading in other languages, the main reason to have them is because of mathematics. Same reason for pretty much anything. When you have overloading, most of the things like for overloading is effectively mathematics. In virtually any other cases, they're not that useful. Seriously. It's because mathematics is generic enough that you want a generic thing. Because the whole point is mathematics is a generic tool. It's not a specific tool. That is one of the only edge cases that this is generic tool. However, most tools are specific, not generic. So that's why it's the outliers of why mathematics is very good for having overloading and operator overloading. That's why people want it. But it's pretty much that's the only case. So the answer is yes, you would also use para poly. This also gets to the same thing. Para, I'm going to try and improve my handwriting here as well. Para poly, which is technically parametric polymorphism, which is effectively called generics to most people. Now the problem, as I was stating, is most problems are specific, not generic. I really need a better one, a bigger one to write on. This is just not very useful. So the problem here is because most problems are specific and not generic, you very rarely need the concept of generics at all. Now that may seem kind of obvious to many people, or like, what the hell are you talking about? But no, sometimes you cannot have a just all parapoly. Sometimes you have to mix parapoly with overloading to get the proper enough genericness in there. Especially, you also need to mix this with mix them with where. Oh God, my handwriting is awful on this thing. I'm gonna have to write a lot slower. Where clauses. Now, this is where things go on a bit weird, is because effectively what you're trying to do is minimize. You're trying to do stuff like this, and it's one of those things where to beginners, anyone, not only beginners, but newcomers to Odin, I should say, that's better framing. Newcomers to Odin, I usually recommend them, don't use parapoly, don't overdo procedure groups, and you'll be fine. Just treat Odin as if it was a better C, and you don't need any of those features, you'll be fine. And it seriously is. It's one of those cases where it's where the things just aren't really, you very, very, ever rarely have a generic problem. That's my point. If that makes any sense, yeah. So it is my issue, the point of view, and you go from generic, you lose the specific, you go to specific, you lose the generic. It is a law of nature in a sense, and it is something you have to tackle with. But it's one way you get your mind on. Usually, and if you keep in things, most problems are specific, they're not generic. And if you go towards more generic, it doesn't work, of course. So this is where things are going to go a little awry. What was the other question? So you're saying, yes, so what if you had like a parameter where said you had like a $t and you were defining it for multiple types? And well, in this case, it depends on how you're doing it. So you could use a where clause. So this is after the procedure, obviously, where, and then you use the intrinsics. So intrinsics, yeah, intrinsics or is it intrinsic? I can never remember what that package name is called. You figure it out in the end, whatever. Intrinsics type is integer. I've just done it again. Integer. And you effectively do that. That's what the where clause is for. And it's a solving because you can't always write a specific specialization. Well, say it's specific of an int or an I32 or a U32 or something like that. You can't always do that. That's a specific specialization. Even though most of the time you do want a specific specialization. Like you may have a type, and it's actually a specialization of any generic slice, and that's what you're defining it to be. And this is what the specialization syntax is for allow for these generic cases. And it may not be even a slice, it may be a generic array when you can put the size of the array in there. But sometimes you don't necessarily want to do that. So yeah, there's another thing here is they're not necessarily needed for math stuff. That is correct. So theoretically I could have, let's say, square root 32. I could have a square root 64. Now the thing is, I want both of these to effectively be separate functions, but when I'm writing mathematics code, I don't always want to just treat them as if that's the case. There's also the issue where I have a square root, and let's say it's an array approach. So if, for instance, it works on every single element individually, but when I call it, I just want to say it's a square root and do the logic as if I was doing that. Now, because it is more of a, that's how you're trying to solve the problem. And you can be very explicit and there's no problem there. But most of the time, people just really want to write square root. And they don't really, and it should just work. It's just something people are used to, and you can't actually get around that problem. Where you can say you can force people to program the correct way, the way I want you to work. But the thing is, that's not necessarily true. Like the way that I program may not actually be the way I'm trying to tell you to program may not be the best way. And this is where, unfortunately, it's a bit of an experience, and it's a bit of, I can't think of the word. It is technically empirical, but it's not actually like, it's qualitative. It's not quantitative. It's qualitative. And you can kind of see how people react to certain things, and that's how they work in their programming. And it's a lot of things like that when I've been designing an Odin, is figuring out, okay, people have been using this feature or this concept or this construct in a certain way, and it doesn't work. Now, you're saying is, can you make it work in a meaningful time at runtime? Now, the problem is, so you're saying, can you do this? Meaningful. Now, the way you get around that, that's really simple to get around. I'm calling that a complex number, and I'm like, yeah, let's just say that's -1, and they've got no imaginary component in there. Perfect, done, no problem. That's how you get around it. No, but in all seriousness, like, that's the problem, is that, yeah, as soon as you start going generic, it starts going bizarre. So for -1, this is a float. So let's say the default for -1, let's say it's a F64. Well, in the reals, these do not support square root, but they only support the square root for positive numbers and 0. They do not support the negative reals. You have to go to the complex numbers to support the square root function. And this is because algebra isn't complete without the complex numbers, obviously. Not obviously, but it's the square root is one of the simplest cases where you can't do a square root of a negative number because it doesn't make any sense. So this, when you go to complex numbers, it makes perfect sense and it's completely complete. And yeah, there's another example. Yes, that's correct. The other example that's useful for procedure overloading is, well, yeah, it's actually technically it's parametric polymorphisms as well. These are the only two cases. It's mathematics and generic data structures. Now, those are the two cases where you want them. Now, you may think, what do you mean by generic data structures? Well, they are generic by define. Like these are, let's say, you've got a dynamic array, or this is a tree, or this is some type of queue or a ring type, or there's different containers you usually have. And these are very generic, and you want to use them for generic needs. In those cases, note the word generic. These are the valid cases. But the thing is, as I keep stressing out, most problems are not generic. The vast majority of them are specific. It's the reason why, I'm not joking, in Odin, I went, okay, most of the time I need these specific generic data structures. I need an array. I want a slice type, which is array reference. I want a dynamic array. I want a string type. I want the integers, I want the floats, let's say, so whatever. I want a Boolean type in there as well. I want a Unicode code point type. What else? There's loads more actually. I want a map type as well, which is map key value. Oh God, there's more. There's more here, isn't there? I need a pointer type. I wanted a generic pointer type as well, which is, it's because void doesn't exist in Odin. It's actually, I'll explain that in a minute as well. This is not me typing tonight. This is me explaining the semantics of a language. What else is in Odin? Oh yeah, I've got the compound types. You've got enum, you've got struct, you've got a union. You've also got the subtypes of these, like raw, union as well. You've also then I've got like stuff like bit sets in there. I've got bit fields. God, my handwriting is awful today. But there's a hell of a lot of things. I just, the basic ones that I built into language, I said, yes, these are what I want. I'll just add them. Now, the only one of this entire bunch which I'm actually skeptical about, and not skeptical, I'm not happy about, is technically the map type. This is the odd one out, because it requires a huge amount of the technically built-in runtime functions, and it's just, don't like it that much in that regard. And also, it's just, I've made it just, there's a lot of things in there, and especially the dynamic stuff's in there. These two dynamic types, I've now allowed it so you can actually just turn off certain features, but it's one of those. So loads of questions here, yeah. So you're saying yeah. And you have a question. It's a bit off topic, but I'll ask you the preference. I didn't graduate computer science. Me neither, because I didn't do computer science. I'm computer programming for more than 15 years now, but recently I took a task of trying to write a programming language. However, I find myself completely stuck after the ST part, and I have a problem even imagining what to do afterwards. Like, I know I need to walk this AST and do type checking, but then what? It's kind of silly, but I'm just all over the place over an AST recursively modifying itself, and it's a little bit at a time. Then run the AST into cogen or write a phase. Okay, so to explain what's going on, we're going to explain it. So when you say you've gotten to the AST part, I am going to assume you have created a parser and you have not created the checker, the semantic checker stage. Okay, so the best way of thinking it is, in a compiler, you have the front end and the back end. So in a compiler, this is in virtually any compiler, actually there's also a middle end as well, but let's explain it all. In a compiler, you have a front end, you actually have a middle end, which not all compilers have, by the way. It's just, and then you have a back end. Okay, so the front end, we can split these up. So we just do this in this case. We have the tokenizer, or it's called the lexer. And then you have the parser. Yeah, and then you have what I call the semantic checker. So what I'm going to do here is just phrase it out a little bit here. I'm going to do the checker. So this is semantic, the semantics of the language. This is the syntax and the grammar of the language. And these are effectively, the technical term is the lexemes, which is where the word lexer, lexeme, oh God, it's tokens. They're just tokens, okay? It's easier to figure out. So they're the things in your compiler. So the front end, you first take your source code, assuming it's a textual-based compiler, of course, and you split everything into tokens. Great, so everything is now turned into tokens. These are much easier to deal with. You then get your parser, and you turn these tokens into a syntactical tree. So this is the AST part. So these are the AST, and you the AST means abstract syntax tree. So this is where you're trying to describe it, and you're trying to describe the syntax of your language in a tree-like data structure. Okay, so a tree, again, just to mean like this, you've got different types like this, and this is a tree. Yeah, whatever, I'm just going to undo that now. Okay, now the next bit is the semantic stage, okay? And then what you're doing is you're adding your data types and your other information, you're giving extra information to the AST, you're annotating the things. Now, again, ASTs are not necessarily binary trees. You can have as many things off them. They're just random trees. Because you don't always want them to be a simple thing. They're just trees in the fact that they don't have any necessarily recursive aspects to them. They're just top down, you can read them. So that's kind of thing. So this is the type checking stage. The next stage after that is is technically the middle end. So the middle end is technically optional. So I'm going to skip straight to here. Well, actually, let's go to the middle end. This is explaining model compilers. So what you're doing is now, once you take your typed AST, you're then going to take this typed AST and then you're going to lower it into what's called an intermediate representation. Okay, so you're going to go AST to your intermediate representation. In this intermediate representation, most common formats nowadays are in some form of what they call single static assignment, or SSA. And this helps you to do optimizations, and then you optimize on the IR. Now, you can optimize on the AST as well. You can do both, in fact. So this middle end is effectively the optimization end, optimization stage, effectively. And what you're doing is optimize on the IR. And you keep doing this, and this is repeated passes. God, I need a better thing. Okay, so that's your middle end, your optimization stage. Then what you do is you lower, this is called lower IR to, now you can either do it to assembly or you're doing it into machine code. Yeah. Then once you've taken that machine code or assembly, you then pass it, you link it all up, and then create, and then you've now got executable. Okay, so that's what's going on here. So you're right, yeah, there are optimizations on the AST as well, and it's not necessarily more better performance on it necessarily. That's not always the case. It is easier because then you simplify the AST, but yeah, you can actually do it as you're doing it on lowering it to the IR. It's actually a bit simpler. So this is the modern stages compilers. Theoretically, you can cut out the middle end entirely, and you can go from the AST directly to assembly for most languages, not all languages, but many languages. Odin, you theoretically could. I wouldn't. But I don't see any reason why you couldn't. It's not technically because there's you got like defer construct in there, and it's not going to work. Which makes it a bit more difficult. But yeah, so that's kind of what you're doing. So that's kind of what's going on. Okay, hello Martin, how are you doing? So first off, I need to get some of the questions, so I'm going to go back a little bit for the previous discussion. Okay, Graphic Master says, as an engine developer, I use a lot of data structures, far more than Odin provides as built-in. In those cases, wouldn't you agree not having a mechanism to implement them with the same sugar as built-in affords is a little inconvenient? The answer is no. And it's a very good question. No, this is actually a philosophical difference between people. So for me, there are some core data types, like some fundamental data types, which every other data type is built upon. And this is, I'm just going to move back to my data type thing. And I'm going to explain what these built-in data types actually are. So ignore, these are container types effectively. So what you have is the pointer, which is obvious nowadays. These are the compound types. You've got arrays. Notice the plural. This calls fixed. You've got slice. You can call this a reference. You've got dynamic arrays, and that's about it. You've got arrays. What else? Other data types are very useful. You've got linked lists. Yeah. Now, linked lists are effectively, you can make these from structs plus pointers. No issue. Basic thing. And I always prefer intrusive linked lists. And there's a huge reason as to why I prefer them. It's because usually when you're using a linked list, the data type you're actually adding it to is fundamentally a linked list construct. Another one you've got here is the map type, which is the hash map. Yeah. What else is there? So linked lists are also related to trees or trees that are effectively the same thing, and you can implement them as structs, and I usually like them being intrusive is the technical term for it, as in they're built into the data type. And what else? Well, I'm trying to think of other things. Oh yeah, so you've got sets, so that's you've got sets in here as well. Lists are arrays. Pools I don't class as technically a data type, because they're effectively a form of array. Matrices and vectors are more mathematical things and not necessarily, I class them not as compound types, so they're slightly different. So every single data structure you have described can be generated from this very, very small set. And I'm not even joking, it's an extremely small set. It's because they are fundamentally the basic building blocks. So in Odin, you think, I want a hash set. How do I implement that? Well, don't look any further. You do this. And you think, what? How is that a hash set? Well, here's the thing. If a key doesn't exist for a map, it returns the 0 value by default, unless you do the comma OK to figure out if it's been set. But if it's not been set, a Boolean is false. It means it's going to be false. If it has been set, you're going to set it to be true, which means then it's going to be true when it's been set. Just by using a hash map, you've now got a set automatically. It's a hash set, done. Odin also has the concept of a bit set, which is for like integer size things, and using like enums or integers inside, just decide what the bits are. But that's slightly different. Again, you just go through the arrays. Yeah, you want fixed. You got slice and dynamic. So dynamic is dynamically allocated, and they expand as you add more stuff to them. Very simple. Trees, yeah, again, linked list. Tries, which are different from trees, but they're not really. Well, they are, but they're not. Again, you can do the same thing. They're effectively, you've got some data structure which has references to different things in there. So you have values and references, value and references. Okay. Let's go through your list again. Variance. So that is not technically union, has it again? So we have union in there as long as struct. These are the record types. And then enum. They're all different types. So they're variance, done. Pools, as I said, are not necessarily, they're effectively a form of array. They're an array of arrays. In many ways, you can imagine that. They're not anything special. Again, and as I said, vectors and matrices and tensors and whatever, they are not compound types. They are fundamental types, which are slightly different for different uses. And you said, you know, it's a small set, but the interface of them is no longer reflects the domain, but the domain of how they're implemented. And there's the difference. I'm trying to, again, this is one of those things, is 90% of the problems I have, not even more than that fact, I don't even need to have a custom data structure. 99% of problems. It sounds, I need a custom generic data structure. That sounds so queer to so many people, but it's like, no. You'll be amazed what you don't actually require. You'll be fine with the basic data types that are in Odin by default, and that's all you'll need, because that is what I've had for experience, and that's my argument. Now, I understand where people are saying this, and this is a good argument. So it's generic. You're going to have, you want some generic ways of doing things, but it's necessarily, the argument is how do you do it? So one of the other reasons as to why I built these in to the language, like for instance dynamic arrays and dynamic maps and stuff and all these things, is so you could get the same syntax as well, which you cannot, and I'll state this, most languages cannot do this, not even C++ and stuff very well. I can go like this, so it could be a dynamic, by the way, this is you can opt out of this very easily. So I have a dynamic int type, and I can actually write it as if it's 1, 3, 5, 7. I can just write it if it's a composite, compound literal, whatever you want to call it, same, compound literal. That works. You can do the same thing here, and I can also write it saying, okay, so the third argument is number 1, the 0th argument is number 2, the first argument is number 3, and the second argument is number 4. And it will work in that order as well. So the thing is, if you were going to support this in your special data structure, how? You would have to go really complicated and complex in your language. But because it's built in, it's very simple, and everyone's got the same conventions, and it will just work. But if you're going to go even further and trying to implement this, you're going to just go, the language becomes so complex, and just complex even from a user standpoint to do it, it's not very worth it. So that's kind of my view. I'm kind of saying these are the practical use cases that 99.9% of cases, programming cases, will actually have. And I could probably say, yeah, it is probably 1 in 1,000 cases and not that. So, go back to the questions. This is back, okay, back now to the compiler questions about how do compilers do their jobs. So Martin had a good question, is where's the part that converts symbols to vars, types, functions, constants that live in the parser? Within the parser stage? No. So actually this depends on the language. So the parser, theoretically, this entire front end can be a single pass. So there are some languages like C, which are technically single pass languages. Now this is, okay, this may confuse people. Let's say, so C is technically 2 languages. You've got the C preprocessor and then the C language. So you technically have to pass it through twice, but you can actually do it pretty well actually. You can actually make the entire thing single pass, so it's not actually that much of an issue. So this is where, let's say they're not single passing, just each you can split up every stage. So first you tokenize everything, so you've got literally an array of tokens. Then you go to a parser, so you turn it into an abstract syntax tree to explain the syntax. Then you do the semantic stage, which is where you type it. This is where you figure out the values of things, the types of them, the declarations and the scopes and the names and everything in there. And that's kind of the general stages of how you do a compiler. Very simple. This is probably going to pick up any book on compilers or anything. This is probably what it tells you, and it's usually the first thing. The next bit, which I'm going to just completely skip, is the middle end. But what you have is now you've got your typed EST. You can iterate it by just going through the tree and looking through the tree, and then you can lower it to your some assembly code or machine code. Usually it's assembly code you're lowering it to, and then you put it through an assembler to turn it into machine code, and then to do the job. And that's where it goes a little bit thing. So you've got the type table, and you're going through and do the operations. So if you came to your AST and it was a binary operator, and it had, let's say, this operation, well, you'd go through your tree and you go, we've got an add operation. So we go, okay, we've got add instruction, and then it's telling us, okay, put a 1 and a 2 in there. And I'm like, okay, this can be put into a register. So you just say what the register is. I'm making up syntax here. So you put register 1. But then you notice, no, wait. This entire instructions was added up. It was actually a multiplication. And then you had a 3 in there. Ooh. So we go through the thing and we have a 3 and a 1 and a 2. So the first thing is, this 1 and the 2 needs to be done first, because this was actually, again, in a parentheses as well. So it was actually a parentheses instruction. Whatever, I'm just making this up as I go along, don't worry. So you do this instruction first. Then what you do is you then go to your instruction 2. You go to multiply 1. Here you go to 3, register 2 from register. Ooh, well, that's the same number. 1, like so. So like so, that's kind of how you're going on. And that's kind of how you're lowering it, and you're doing it slowly, step by step. Okay, you've got a tree, it's got these parameters, and you're lowering it like this. And that's what you do in register. Now, why most modern compilers go to an intermediate stage is one thing about SSA is it's single static assignment. Each register that you're assigning to is unique. So then you do all the optimizations that way, and you make sure none of the registers are being reused. And then once you're done with all your optimizations, what you call color your registers. So this is actually a called a graph theory thing. You're coloring it, as in you've got a small selection of registers, and then you want to transform those registers into a certain set of what the number of registers got. I mean, say you've got 100 virtual registers, but you've only got 8 real registers. You need to color it so they don't get reused and they don't overlap and stuff. And sometimes it's not actually physically possible, which means you may need to go into stack memory to allocate the things that go into registers and do it that way, so then you get to them back later. Sometimes it's not always the case. You can't color all graphs. Okay, I'm going really technical now. Sorry, I'm kind of confusing here. I'm going all over the place as well. So yeah, more questions. So I'll go back to let's skip that one for the time being. Let's keep on the compiler stuff just for the time being, so I don't keep skipping people like mad. Wouldn't a map to a bool use extra memory? The answer is not necessarily. That may sound bizarre, but not. It depends on what the key type is. So theoretically, it might not use any more memory, because if the key type isn't that big, the bool might just be it just takes into part the padding anyway. But if it is big enough, then yes, it may use extra memory, but it's not necessarily an issue. You're literally probably you could be wasting 7 bytes per entry. You might be, but it's probably not that much in practice. But yeah, and again, okay, syntax overloading eases writing code but makes reading a little bit cumbersome. That's correct. Anytime with you will go to generic, you lose the specific, and generic is less clear than specific, always. This is, again, law of nature. It's how it kind of works. Okay, so the other question from Martin again is, okay, so where exactly do you turn names to vars, types, and constants declared? That is, where do you turn names to? What do you mean by names? So I'm going to write this down. Let's say we have Odin, okay? So Odin, when you're doing let's say a variable declaration, you're doing this. You have x : int equals 1, 2, 3, and then I can do x plus equals, let's say 2 times by x. Well, that's not what it is, but let's make it an actual 2 times x minus 1. semicolon, semicolon. Okay, so let's go, and I'm going to change the color. We'll go red. So the first stage, I'm going to do red, green, and blue to express every single stage. So, oops, whoa. I think I've just accidentally opened 20 different file explorers at once somehow. That is impressive in my opinion, but I don't know how I did that, but I did. Okay, so the tokenizing stage I'm going to call red. How do I... We have green. Oh, you have to just use it first. Okay. And then that's a horrible color. That's not good. Let's go magenta. Yeah, that's nicer. Okay. So first off, we're going to split this off into tokens. So the first thing is a token here. We've got 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 a token here. And we've got a token here. Token, 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 token. Dead simple. So that's what you're doing. You turn them into tokens. Next, we are then going into the semantic stage. And what we're saying is, okay, this is a declaration. So we're saying this is a value declaration. And then what we're saying here is an assignment statement. Okay? So we're doing this. And the way that we'd pass this is obviously we're going through, okay, we've got this X, okay, so it's an identifier. Then we notice a colon and we go, okay, we're going to expect a type now. And we know this is a value declaration from the colon. Okay, we're going to pass a type. And in this case, it's just an integer, so it's very simple. Then once the type has been passed, we're expecting either an equal sign or a semicolon. In this case, we found a semicolon. If that's the case, we then look for the expression, and then we expect a semicolon. Very, very simple. No problem there. So that is how you store it. That's just storing it. Then once you've stored it, so this you could effectively call it X. You've got int, and then 1, 2, 3. So that's the name, type, value. Yeah, no problem. Or you can call this, instead of value, you could call this expression. But let's call it value. Yeah, makes sense. Next one we've got is this assignment statement. So we have a left-hand side, the operator, and the right-hand side. So in this case, we've got a left-hand side, which is an X. We've got an operator, which is the plus equals in this case. And then we also have the right-hand side, which is this expression here. Now we're going to write it as if it was a tree. So that's 2 times X minus 1. And then we have this. Let's do that. Yeah. So you can see we've got 2, and this is the tree that you would write. And that's how it would work. Okay? So that's a binary expression tree, and that's how you would pass it. So that's the syntactical stage. Next, we're going to go to the parsing stage. So we're going to, no, it's not the parsing stage. This is now the semantic stage, yeah. So we've done the parsing, which is syntactical. Now we're going to semantical. So the first thing that we do is we notice we've got a type, and we look up within our type table. This int thing corresponds to, and guess what? An int. We then check the expression of this, and it has an expression and a type and a value. The value is 1, 2, 3, and an untyped int. We then check to see if this value is assignable to an int, and if that's the case, it's fine. No problems there. If it's not, it's going to fail. Then once we've got this, we then sign X and say X has now got, we're going to add X to the scope. So X add to scope, the variable scope. We're going to say X has type int, and it has initial value, so init value of 1, 2, 3. That's the semantic stage. Then the next stage that we're going to do is this thing. So we find this, we have this expression X. X in this case, we look up on our table, and guess what? This X refers to this thing. So we found it, and we know it's got type int. We then evaluate this right-hand side as well. Yeah, so we go, okay, this has a value of 2. This is X again. So we found that, and we found 1. And then we look through the code, Okay, and we've typed it all up. And then the entire expression of all this is actually an int. So this expression's an int, there's an int, there's an int. So this entire expression is an int. Then we go to the thing and we check to see if they can add up. So we've got an int on this side and an int on this right side, and they're absolutely fine. So in this case, the stages we have, for Odin at least, it's not technically all the stages, but it's not technically true, but in this particular case, this would be number 1. This is number 2. This is number 3. This is number 4. Number 5, 6, 7, 8, 9. And they're all the order, and then we've got a 10 here. 10. Their order of the stages. So that's the semantic changes. So each piece of the node, you give the types and maybe even the values if it's a constant, and the associated, also if it's a variable, you associate it with the declaration, because I've just declared a variable called x. Hopefully this now makes sense. I'm trying to explain a basic compiler. I have not planned this ahead. I'm just doing this off the top of my head. If you want to learn how to actually write compilers, I usually recommend Niklaus Wirt compiler. Now, it's luckily the book is for free now. This is Niklaus Wirt compiler construction. I usually recommend this because it's usually clear to understand and it goes through every single stage of the compiler. And you're making a programming language called Oberon Zero. So this is a stripped down version of the original Oberon language. There's Oberon 1 and 2, of course. This is Oberon Zero, and you're going through what everything goes through, and it explains everything about trees and how you would parse it. Like, here's the A times B plus C, and you see A, oh, okay, here's what it is. And each different thing gets parsed slightly differently, and you can see how it works. And it's a bit of a deep dive into things. Some of this is also, I recommend Wirt's book and stuff, and if you can get it, algorithms plus data structures equals programs. You can find that, but yeah, you can see all these different things. It talks about different languages. It's a bit heading, and again, it's written in like old Pascal stuff, but Pascal's very easy to parse, so that's usually quite a nice thing. And then they're talking about how to do the programming language here, and there's probably more stuff if you find it with the disk. Oh, we got a disk. Oh, that's too expensive for most people, so don't bother with that. Don't spend it. You can get it for free now. But yeah, that's another wise thing. So let's go back to the other questions that we are now talking about. So yeah, another question here is back to Martin again. It is, and semantic stage is done where the stages you've drawn. Yes. Also, does the semantic stage produce an AST tree or mutates existing AST? So the semantic stage does not produce the AST. The parsing stage, which produces the AST, the semantic stage mutates the AST, as in it gives type information and constant information and many other pieces of information that you do as you're going through the semantic stage. The AST, the parsing stage, just generates this AST that you can then, it's a scaffolding, which then you can add more information to, more semantic information. When the semantic information is full on the AST, you can then go and lower it theoretically, for many languages, to the assembly or a machine code or whatever. Then do a linking on it and then create the actual executable. Or you can do optimizations on that AST that's been checked, because now there's actual information on it and such. Okay, so back to some of the questions about the generic data types. So from Graphite Master again, I can't pronounce Graphite Master, sorry, I'm not speaking very well. Like, if I'm working with spherical harmonics in my engine, I want a vector that describes the n-order spherical harmonic and the interface of that to follow the mathematical domain of what spherical harmonics are, not fundamental compound types that have no relation to it. My argument is, no, you don't. That sounds like you're just copying out what you're doing, what you're talking about. No. So for me, when you're actually making programs, I never forget that I'm working on a computer. You might like to want to have these higher level constructions because you might think that they may help you. But at the end of the day, you're still working on a computer, and that's the actual problem domain you're working in. So a spherical harmonic, at the end of the day, isn't actually that... I need to write it in because I can't remember all the number of parameters you actually need to describe a spherical harmonic. I think it's only, is it 2 or 3? It might be 3. Yeah. So spherical harmonics are effectively, let's explain what spherical harmonic is. So spherical harmonics. Actually, shall we go back a stage and let's explain not spherical harmonics. Shall we go to 2D? Because technically you can have circular harmonics, but no, let's go for 1D. So 1D is the Fourier series. Okay, so let's go to 1D harmonics. Okay, because spherical harmonics are technically a form of 2D harmonics. They technically are not 3D, they are 2D, which confuses people, but I'll explain why. So let's say you have some signal that repeats, theoretically. Let's make it simple and say it repeats, and it's you've got some parameter phi in there, whatever, and your signal looks like this, and then it does repeat again. What we have going again, this is what Fourier proved, is that your signal here, signal of theta, can be expressed as the summation, and now this is not actually how I actually do it in my head. These graphics are terrible, thank you, but whatever. Let's go back to yellow first. I preferred the yellow. Let's do the theta. What this can be expressed is, you can express this as an infinite sum, or any sum, so let's say I to that to infinity, of different variables of cosines and sines in there. Yeah? And theoretically you've got I've missed out some variables here. So we've got theta and let's call it theta and ki as well. Yeah, so it's an infinite series of fucking hell, I've confused that again. Whatever, that's not even a good Fourier transform, is it? Because that's not actually how I think about Fourier transforms, by the way. Because it's so Fourier transform, I wouldn't actually. There's the way I'd normally think about it, and then the way that textbooks teach it, and the way I think about it is actually a little bit probably more high level. Yeah, let's just explain it. Let's just go the full blow, and let's just explain it the proper one. Yeah, so Fourier transforms. These aren't Fourier transforms, these are Fourier series. Sorry, what am I talking about? Sorry. It's close enough. So you've got a Fourier series. So there's the two ways you can explain them usually. So let's say you got some function x. Yeah. Your Fourier series, you can express this as some, again, usually you've got a constant here. So you call this the A0 term. And then you've got infinite terms of n equals 1 to infinity. And then you usually have your n term here of cosine kx. K is some constant. And then it's usually knx here plus another variable which you call b sine of knx again. Yeah, that's your Fourier series. Now, the way that I personally think about Fourier series is that I don't use this. You just simplify it entirely. You can literally simplify this entire expression. And there's actually two ways of doing it, in fact. You can get rid of the sign and just put a phase parameter in there. But the easy way that I usually think about the Fourier series is like this. And then you just completely ignore this approach. And you just go n equals negative infinity to infinity. And then you have some constant. This is literally a complex number of e to the I k n x. Done. And this is the complex approach to it. And it's a much simpler way. So it's just a simple, it's infinite sum of these, literally sine waves and cosine waves, effectively, yeah? And that's what you're doing with a series. So this is a 1D approach of, you can represent any signal as functions of sines and cosines. That's all you need. So that's 1D. Right. Oh, goodness. Let's now go to 2 dimensions. So 1D, the way I'm thinking about it is, notice let's make sure this is clear. Most signals will repeat. They're not just things. And the Fourier transforms effectively have got this repetitive nature to them because the cosine and sine, they repeat. So they will repeat theoretically, even in infinity, but let's not go into the philosophy of that. So what you can technically imagine this is that a Fourier series is on like the ring of a circle. Like this, yeah? It's on the edge of a circle. And let's change the colour. Your signal is going across the edge of this ring, and it repeats as you get back to it. And it's unique for that loop. Okay? So then your Fourier series explains how much of each component you've got. So your signal may have, of A0, it may be a single, say it's got a value of 1. A1 is like 0.5, A2 is like 3, whatever, and then you've got your B notes as well, whatever. So technically I'll just call these C's. But your signal has got all these different components to it, and they're expressing all the different values for your signal. And if you want to approximate your signal better, you just drop off the higher order terms. So your first approximation may look like this. Your second approximation may look like this. Your third approximation may look like this, if you keep adding them on. And then the fourth approximation, you do this, and then dot 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 to infinity. It may just be you've got a square wave. And then that's what you're doing is, so you're doing different components. That's your 1D case. So now let's go to 2-dimensional Fourier series. Now, what most people call these are spherical harmonics. Some people in the audience are going to tell me, no, they're not technically the same. You're not talking about this correctly. Sorry, that's you in the audience. That's what you sound like to me, don't you? This is exactly what you sound like. Great, isn't it? No, so spherical harmonics are effectively these different signals of, you've got something going like a loop, and you've got this band. So imagine the first one is like a rubber band and it's vibrating, and you've got a signal going around that rubber band. For spherical harmonics, it's effectively what happens if you had a ball, and the surface of that ball is vibrating. Okay? And you can express those vibrations as different components of the spherical harmonics. Now, notice I say 2 dimensionals, but I've just said a 3-dimensional spherical ball. That's because I'm talking about the surface. So in this case, it's a 2D manifold. Yep, I'm going down into the mathematics here. So you got 2D manifold of the things that are going on. Yeah? So that's where it goes a little bit fun. I've technically skipped a step. I should just go back to 1D. So the 1D is each of these components, by the way, they're called orthogonal. So if you know your calculus correctly, what you can know is when you've got an orthogonal function, it's not, if you've got let's say a function of b and function of t, dt, if they are orthogonal, they'll equal 0. Is that correct? I think so. So an orthogonal function is that they don't affect each other. An effect that, is that right? No, I'm probably fucking that up now. Are they orthogonal? Trying to think this through. Yeah, so no, that's wrong. So what it means is these are orthogonal is if you can pretty much separate them usually. And they're not necessarily separable, but they don't really interact with each other. You can keep adding them and it doesn't affect the original thing. Makes any sense? You can usually see what I meant when I was trying to make a square wave and just adding more and more sine waves on top. Makes sense. So the spherical harmonics are another set of orthogonal functions, and they can form an orthonormal base. Again, and most people don't know what we're talking about. Please check up these terms. Make sure you get to use some book. Now, the spherical harmonics are technically expressible. You can express them, and they're normally written in M and L. So you got an M and an L parameter. Actually, it's technically about there usually. That's not an L. That's an L. And then you've got these different parameters. So x, we had an x, but you could do a theta, which is harmonic, and then you have usually a theta and a phi. That's not phi, that's a phi. And then, or sometimes, or you can usually write it as some vector r, which is like x and y components. But yeah, or explain this. It doesn't make a difference, but we'll explain this because you can see there's two components. So you imagine you've got your sphere, like so. Each point on this sphere has a unique way of expressing it in theta and phi. So this is theta and phi on that point on the sphere of a unit sphere. Okay, so a unit sphere, like that was a unit, like you can say it's a unit circle. It's a unit sphere in this case, okay? If it wasn't a unit sphere, you can just take out the constant here and just scale it and just make a difference, yeah? So these are what these spherical harmonics state. So these are these they're orthogonal when you do integration with them and stuff. They're orthonormal means then they're always a kind of like size 1. And orthonormal means they're orthogonal and normalized, so you make them basis parameters. Hopefully it's making some sense. If it doesn't, just tell me. So the spherical harmonics, these are these Y things, which Laplace kind of introduced the terms. This was back in the, late 18th century, I think. I haven't touched this in ages, like the actual technical stuff. But what Laplace was trying to do was effectively solve a Laplace equation. He invented them, of a scalar field in spherical coordinates. And so I'm trying to think how I'd explain this. I'll just explain this. When I'm going on a bit of tangent here. When I learned about spherical harmonics, a lot of chemistry started making sense to me because I was learning at the time. I was learning about spherical harmonics, about quantum mechanics and stuff. And all of a sudden, oh, atomic orbitals. That's why they have the shapes that they do. They're just spherical harmonics. Oh, why did no one tell me this before? Yay. But whatever. So if I can remember correctly, and I probably am, this spherical harmonic function, which is each parameter, which notice we've got an M and an L here. Previously, each one of them, we had an N parameter. So this one is effectively here, you've got a summation of all of them, whatever, of N. And then what you've got here is some function, and we can call this a Fourier series of f of n of x. So that each parameter n has got a different component to it. Hopefully that makes sense. Yeah, no problem. Good. So that's f of n, and technically you've also got a parameter k in there as well, which is just some free variable. In this case, you've got m and l, which is slightly different. They're not the same. So if I can remember correctly, you have two different sets. You can actually expand these. So you've got your m and you've got your l of theta and phi, and you can usually expand them into this form, if I can remember correctly. I haven't done this properly in years. I just know how to use them. Yes, that's a cosine theta there because it maps easy and it makes the maths a hell of a lot easier to do. And this is the Legendre polynomials, and my French accent was awful there. And you'll express them in slightly different ways here. So you've kind of got your separate, and you notice they are kind of separable as well. So your m component here is different to the l component as well. A lot, yeah. So you've still got this I to the theta thing here, which is similar to the what's it called? That is different to the God, I can't even think this through. Like to these the one-dimensional ones I was talking about, which is the Fourier series stuff. Yeah. Now, what I mean is this phi, I'm going to write it out like this. Yeah, just screw the M and M notation. It is actually separable. You can assume it is separable at least. And what they normally do in textbooks, if I remember correctly, is you assume it's this. and you can do the equations. Because what you're trying to effectively do is the Laplace thing, which is where you're trying to figure out the Laplace function. The Laplace function here is not going to vector calculus. But if it was in Cartesian coordinates, so Cartesian, this is pretty simple usually. It is the this is it's the plus function, and then what you're doing is effectively the df dx squared, dy squared and df dz squared. But we're in polar coordinates, so it's a hell of a lot more complicated. And you can start figuring it out. Now, I think if I remember correctly, it is something like that. So that's your radial part. In our case, radius is just 1, but doesn't make a difference. So this just actually simplifies down a hell of a lot, by the way. And then you have your phi part, like so. Oops. D phi, and then you've got your sine. I took that through. df by d phi. God, I'm doing vector calculus, and this is not order. Sorry, this is bleeding all over the place. And then you've got the other component again, which you have to. This 1 over r squared sine theta pops up again. I remember now. And then you got your your d. That's the sine squared now. This is sine squared because you've got an extra component in there. And then luckily, you don't have to have this extra thing in there. The d phi squared pops up again. And then that's what you've got for your Laplace function. Now, what Laplace was trying to solve with the Laplace equation, now Laplace's equation is slightly different. It's saying Laplace's equation is this, equals 0. So he is trying to find a function, f, which satisfies this entire series of stuff, a generic one, by the way, which equals to 0. Okay? So that may sound a little bit like, wait, no, it's true. Okay, so let's ignore all the theory of how you derive them. But what we have here is you effectively are doing the same thing. So I've got I just found a little thing on the internet for you, which is probably actually very good. This is explaining like spherical harmonics for two-dimensional surfaces. So the most simplest one is, of course, the sphere. This is the surface of a sphere, and it's just stable. There's nothing going on. Nothing else. That's just your thing. The next oscillation you could have are the p orbitals, obviously, and these are the things that vibrate. You can imagine these go vibrate in and out, and they make these patterns. They can go or up and down, or back and forth. There's 3 axes that they can kind of oscillate in a sense, and they're all the same kind of thing. They're just slightly different orientations. The next mode is you've now, instead of just having 1 rotation, so 0, you've got 1. Now you've got 2 axes of rotation you can do. And notice they've got, these is why you get these weird, funny patterns if you ever did chemistry and you're like, why are the orbitals that shape? Well, this is spherical harmonics for you. This is how actually those surfaces kind of how you would vibrate. Then the third mode, you have 3 modes going on. For 4, you've got 4. For 5, you've got 5. For 6, you've got these 6 now, yeah, obviously. Now notice this M parameter, as you're going down, which is the L, this is your L parameter, your M parameter gets wider, and it's wider by, if I can remember, it is 2L minus 1, if I can remember that correctly. Or is it 2L plus 1? Yeah, it's 2L plus 1, so it's 2L plus 1, how many there are. And that's kind of what's going on, if that makes any sense. So the thing is, any kind of these patterns in 2 dimensions, how much like intensity you've got the surface maybe, or how much is vibrating or whatever, if you add every single different component of all these different spherical harmonics, you can rebuild any signal like that repeats. It's the same with like a Fourier series in 1D, spherical harmonics are the same in 2D. So where Graphitmeister says he only knows spherical harmonics with respect to diffuse lighting, used for approximating the value of diffuse lighting at different directions but stored as one vector. This is an inference series, yes, you cut off. Like I was saying previously with the Fourier series here, you can have different approximations. This may be your first order approximation, second order approximation, third order approximation, fourth order approximation. And as you get it, it has the higher signals and the higher noise goes up and up and up. And you, when you're doing that, it shows that you can cut off some of the noise to reduce some of the data. But as I said, each signal, each phase in the signal here, you're pretty much expressing it by probably one number, just one number. In this case, you're expressing every part of the signal by two numbers, if not three, technically, actually three for numbers, whatever. And then the higher order components, which again, they're orthogonal, so you can do it, the higher order components, you may be cutting them out because you don't need them and you can approximate it pretty much well. So this is where in for like lighting and stuff, spherical harmonics are a very good example, because think of yourself from the viewpoint of an expector and you're in like in a sphere. And every point in the sphere has a certain brightness level to it. Well, you can start approximating, building up these spherical harmonics to do all of these different things. And it all kind of fits together. It's very, very, it kind of works very well. And that's the whole point. The practical thing is you don't need the infinite series because you only want to store as much data as you can. And you usually stop off, as you're saying, you stop after about the third order. There's no real need to go any further if you just want to approximate it. But yeah, that's effectively what you're doing. So in 1D, you've got your Fourier series, Fourier or Fourier. Actually, you know what? It's Fourier series. That's what it is. That's what I'm going to do for it now on. And you've got some function of theta, and this is effectively the infinite summation of some complex values of e to the I kn theta. Actually, Fourier series. In 2D, you have your spherical harmonics. And then what you're doing, we say you've got some function at theta and phi, yeah? It is technically now the infinite series of and L. Now you've got two free components. And then you've now got your spherical harmonics. You've now got the different ones, so M and L, you know the constant here, of your spherical harmonics at that phi and phi. Yeah? And that's what's going on. Okay, and that's what's going on here with everything you're doing. So there's technically a even higher level one, of course. You could just find another set of equations. By the way, these equations are not the only orthogonal functions you could ever use to build any signal. They're just usually the ones that are conventionally used and just the simplest as well. But hopefully this is explained a bit. This literally, I wasn't even prepared for this, so I would have prepared it. Yeah, I know, it's nothing, again, yeah, nothing array with arrays of 100, yeah, you're right. Wait, let's get to that now. So we've now explained the theory of explaining what these are, okay? Right. So now we have the theory, we can say how much they do in it. So each component that we've got up can be expressed as different numbers, obviously. So the question is, what is the data that you have? This is where I'm saying the data structures. Your data structures, not being rude, what are you actually storing? Because to me, for the 1D example, let's say you've got a series and you want to approximate it. Let's say you've got a series here, I'm going to say you've got a vector, you've got an array of some numbers here, and each number you've got a different constant. So the C's, let's say from 0 to in the range of what's your C vector, which is this bit here, is effectively going to be First off, let's just go for 1. C is going to be an array. I would say it's going to have 1, 0.5 minus 0.3. And let's say it's just add another approximation of the constant in here is 0.5, whatever. I'm just making it up. And that's how you express your signal, and that's how you can do it uniquely. It also has a frequency to it here, and that frequency could be, let's say, 0.7. I don't know, made it up. Now for 2D, you have actually still got this constant, but it's now a little bit more complicated because you've got this M and L parameters for each of them. So you effectively got a vector of vectors, it's a matrix. So you may have different values in here for each of them, whatever going on, and that's how you build it up. So as you're saying, you've got a vector of 16 numbers. Yep, I've got a vector here. Okay, so I've got an array type. So what data type do you need? I'm seriously asking, what complicated data type do you need for your practical case? Not your hypothetical, theoretical case where you're doing all this geometrical, this like abstract algebra, sorry to say. But like your vector case, you're actually just got some coefficients, which are probably complex as well. So they're complex vectors or matrices or tensors, whatever you're doing. And that's all they're expressing. And you already have the components at each function, each point. You're just adding them up, actually how much they add up to the actual final product. So as you said, to the third order, this was the thing here. Third order is just your F orbitals. So this is all, these are the full set of your orthogonal functions. You've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 functions effectively. And they said you got the 16 vectors. So each of these is 16, and each of them has a complex coefficient to each of them, to how much they're contributing. And that's it. So I ask again, where's your complicated data structure? What specific thing do you need? Because all I'm looking at here is 16 complex numbers that you're storing. That's it for your F orbitals, up to F orbitals. So implementation-wise, it can be defined as an array of coefficients, but interface-wise, that is poor to work with. You have algorithm procedures that operate on them, and there's no way to properly associate them with the fundamental data type in a way that behaves like the algebra in math would in the model of the domain. Yes. So let's go back to the thing, and there's a reason why I actually said the word Fourier transform earlier. This will sound quite interesting to people, and some people may not know the noticing if you just know the practical uses, you not always know the theory. These coefficients are technically your different components. Now, I was working in a discrete space because I'm assuming computers being in a discrete space, whatever. But each of these are effectively different frequencies, and these are frequencies and their signal. So your signal may look like this, and this is in. Let's say this is time, and then this is your x position. When you're break them up into your components, you're actually doing a Fourier transform as well. You are actually doing the Fourier transform, and this is the Fourier transform of it. Yeah? And when you go to the Fourier transform, you're still keeping the time as the base, but now you're going into K space, which is it's frequency space effectively. Let's just say it's frequency space. Let's call this frequency space. And what you're saying is, okay, you got this much of this component, this amount of this component, that much of that component, that much of that component, and this one, this. And that's if it's discrete. It might be, if it's not discrete, you've got something that looks like this, and it's actually we're not doing negative because that confuses people. Let's just say you've got something like this, and then you've got your thing. This is what, if you're doing like EQs, and if you've ever seen them on like a thing, that's what they're working in. They're working in frequency space, and you're seeing these how much at different frequencies you're at. Yeah. So this would be your frequency, and then as you're going along, it's not the time anymore. You've got a frequency here, and your k space, okay? And you've just kind of swapped coordinates. So you've gone, whatever. It's not frequency anymore. It's still time, and you go into k space. Whatever. I'm confusing people. I know I am. Because you're doing... yeah, well, no, I was right. Sorry, it's frequency, whatever. And then you're just doing that. Whatever. Screw it, I'm tired. It's nearly midnight. But yeah, that's what you're doing, is breaking up. Now, the spherical harmonics are actually the 2D equivalent of what you've just done. So as you're stating, it's a very poor way of the interface of it. But the thing is, what are you trying to interface? Usually when you're doing spherical harmonics, you've actually already got... Oops, sorry, I've just knocked the microphone stand again. Sorry for the dang. You've got you've already got an image of what you're trying to represent. And then you pass the image in, you've got your algorithm, spits out the vector of the 16 complex numbers that you want to compose into the spherical harmonics. There may be reals as well, I don't know. And then you add them all up, do the functions at each single point, and done. Because effectively what you've done is a Fourier transform, but in 2D. It's a 2D Fourier transform. For the surface of a sphere or a 2D monofold. But this is what I know what you're saying, but the mathematics is simple, because the practical case is you want to turn something and represent it in a simpler form in spherical harmonics as approximation. But the user, even the programmer, is like, no, it's an input and an output, done. So I know where you're coming from your argument, but I don't agree with the philosophy is what I'm saying. Yeah, sorry, on this complete tangent, we've gone from programmers to programming. Actually, what did we start with anyway? Oh, look at that. I didn't realise I zoomed in. That's actually kind of funny. So that was not started. They were talking about overloading and all that stuff. We talked about random crap there with square roots and dynamic variables and compilers and Fourier transforms. And then we zoomed in a lot for some bizarre reason. And then we talked about all this crap. Yeah. Yay. There we go. And that's kind of how spherical harmonics work. But I recommend people highly read them up again in different books. And Wikipedia art is never a good start. But yeah, it's always good to make sure you properly learn about this, because it is pretty damn useful. Yeah. Yeah, you're right. I wasn't going to do the thing I was planning to do, which is make a mild, pretty printer for Odin from the AST, the parser thing. Yeah. Yeah, sorry, I just don't know. I can explain. I know spherical harmonics very well. It's quantum mechanics, man. You had to know them to understand how a hydrogen atom worked. And when I did, I understood chemistry. That, and also I need to know Gibbs free energy equation. Those two things together, spherical harmonics and Gibbs free energy equation. Yeah, most of chemistry makes sense now. I know you don't get taught that when you're like at high school, but it's a hell of a lot. Yeah, that's a whole semester in 1 hour, I know. But I'm trying to show you the gist of it. And the thing is, you don't actually get told the relationship between Fourier series and spherical harmonics. Because it's either meant to be assumed you figure it out, or you don't actually, people don't realize that. And that's the way I think about them, is they are effectively the same, but apply to different domains. That's why I said the Fourier series, you can think of it as the edge of a circle, and it's the vibrations on that circle. You can call that like a string or a rubber band thing. And then for the spherical harmonics, it's more of the vibrations on like the surface of a sphere, that sort of thing. So the three-dimensional thing would be the surface of a hypersphere, which this is okay. Here's the fun bit. Okay, this is where most people don't realize. So for Fourier transforms, it's effectively you're explaining them with complex numbers, right? For spherical harmonics, all the components are actually two-component complex numbers. So wait a minute. If anyone guessing the thing, what's a two complex numbers together? Like you've got or four reals maybe. What else could you explain them with? I'm thinking. So if a ring is explained by complex numbers, and what's this surface of sphere explained by these two complex numbers at each point? Two complex numbers. I'm going to wait until anyone in the chat can figure that out. If you can figure it out. I'll write it out slightly. I'll write it out. So 1D is you've got complex numbers, right? Which is you've got x plus iy. Each component is that. In 2D, which is this is Fourier Series, this is Spherical Harmonics. It's a component plus a complex number. So you've got an x plus iy plus the z plus iw. Hopefully this is making people realize what I'm about to figure out what I'm saying. Because there's just two sets of them. This is one I actually figured out. I actually remember figuring this out when I was doing physics degree. I went, oh, this is damn cool. I figured out how to do it. No one. I'll give you a hint. You can write it like this. It's called quaternions. So but yeah, so you can technically do that. You don't actually have to. Yeah, they are technically rotors. Yes, you're right. But you can actually express them as quaternions. There's no actual difference in this case. They are actually isomorphic, so it's not a problem. Yeah. So, but the thing is, they are the components, so actually they're not true. So this is technically two-component reals, and then this is a two-component complex. It's technically that. But you can express them because they are isomorphic, so it's not a problem. I'm covering so much. Yeah, so the higher order stuff, it would be, if you were going to higher level stuff, you're effectively looking for a map where you can go to the complex numbers as well. So the spherical harmonics, as I stated, are defined as kind of complex numbers on the unit sphere S2, but they're inside Euclidean three-dimensional space. And of course they can be generalized because you just need some orthogonal functions and keep going up and up. This means, yeah, you can lead to functions which are even higher in different higher dimensions. So Rn goes to, I should make sure the notation's mostly correct. Surface of a sphere, which goes to other complex numbers. So each of them can have a complex component to them. So what you've effectively got here is your mapping to the complex numbers. Yeah, sorry, I'm confusing people now, I guess. Sorry. Yeah, you can go to high dimensions, but I haven't actually ever needed high dimensional spherical harmonics. Ever. I can't really think of a use. Oh, I can't. Well, I probably could think of a use case. Actually, the use case I can think of is insane. But yeah. Yeah, the use case that I'm actually thinking of is actually insane. So theoretically, you could have a 3D space which you represented by these higher level ones, and you can take approximations of a 3D world that way. Because what you're doing is you approximately get a four-dimensional thing, but you can treat four-dimensional space as 3 dimensions plus 1. So you can have, this would be your x, y, and z, and then this is your density parameter, effectively. And then you can just treat it like that, and then you've got a 3-dimensional space with density and how much the spot, and then you've effectively got blobs everywhere. You can think of it that way, and think of it that way. That is another way you could do it, but I'm now going to insane territory, and this is what happens when I go tired. I'm talking about random crap. Hey, you didn't break me, don't worry. I go on random tangents. It's fun, okay? Look at that. Also, whee! Yay! I was explaining stuff. I don't think I'm going to do the same thing I was going to plan to do. Who cares? But I wasn't. This is so ad hoc, and I've had to apologise. Like, I don't remember any of this. I haven't touched like the actual theory, but it's. But once, okay, if you can understand what I was trying to say, yeah, it makes more sense. So as you was again going back to your original point about the data structures, well, effectively you've got a list of coefficients. That's what you've got, and that's it. But how you get to that list of coefficients is more complicated. But effectively, you've got a procedure, an algorithm to get, and some data to get to the things. That's the interface. I have not, for that particular case, there is no complex data structures that you needed. That's my point. Nothing like specific you needed. So that was all I'm saying. Yeah, I need a better graphics tablet. How old is this graphics tablet? Doesn't tell you the year on the back, does it? No. Apparently not. I'm going insane, but it's got patent numbers on it. FCC tested to comply with FCC standards for home or office use. Nope. Nope. It doesn't tell you. Isn't that great? Well, if they told you what year it was main came out, people are like, oh, I want the latest one, please. Oh, so your argument is if that coefficient listed thing has its own type and its own interface, you can use mathematical operators for summing and transforming, all regular vectors do. So your argument is have array programming, which Odin already has. But yeah, I'm not joking. I know what argument you're trying to make, but it's more of a, you don't need the special operators really to do that. You can just use procedures for that. And not just that. It's not something that you're really using all of the time either. Seriously, I'm more of a person who goes, that doesn't really make much. Like it's I'm not a big fan of operator overloading in general because it's not even needed that much. Even for like stuff like that, a function is clearer about what is actually going on when you're doing it. Because you're saying, okay, we're adding the components of this spherical harmonics together, or you're averaging them, or you're finding the difference so you can find all the other stuff, whatever, yada yada. Yeah, it's custom stuff. It's non-intuitive, so if you did the add operator or the times operator, most people wouldn't know what you're doing sometimes. So having a function is actually even clearer in that case. So a call doing, let's say, if the call literally went, I need to get back my graphics tablet again. If the call went foo ... we'll say x, y, better than doing this, because I'm like, what does this thing do? It's magic. But this is very descriptive. Now, it's also verbose. This is terse. So you've got this compromise, and everyone has to do it. I would say I'd rather be verbose in most cases when the terse option is non-obvious. That's all I'm saying. It's the reason why I hate, like many people I've seen in C++, they'll do this for vectors, and this is meant to be the cross product. It's like, I know, all right, you're saying you should know what plus is if you know your domain correctly. And the thing is, no. And I know that sounds bizarre. That sounds like a really thing. It's because you're being even more specific to your domain. And sometimes it's just not. Like, you're having a general purpose. If you're having like a very high level language, it's not a problem. But Odin isn't high level. It's very general. So it doesn't have those. It goes a little bit. I'm just repeating myself. Yeah, the types is out. That's a good question. The purpose of the types is to describe the domain. Yes and no. Welcome to where it gets complicated, and this is going to philosophy talk. Yay! So, what are the purpose of types? Is a good question because it depends on how you look at the things, and I know how you work, Graphite Master, and you know how I work when we think differently. So you're thinking of types as more of a way of sets of operations for that thing, and you're restricting it as a set theory-based thing. As I've explained before, that's how you think. And I know how I think. For me, I'm more of a type theory person that thinks that a type is more of a setting. This is a domain of different operations in general, and then it's not a set of them, but this is kind of how it restricts. It's the opposite way around. It's kind of the dual of each other, actually, in many regards. So when I say the type of an integer type, it has a certain set of operations to it because of its type. Yeah, it has a certain amount of different set of operations, yes. But the set of operations doesn't define the type. The type defines a set of operations, which is the opposite way around. I know sounds like the same, but no, it's one implies the other. It's the directionality of it all. You can say they're equivalent to each other, which is fine, but they're not technically. That wouldn't be isomorphic. They'd be hot. They say, "Oh, it's more homomorphic." I don't know. Those words always confuse me. I don't remember. I want to go there. But so where it's very complicated with types because it depends on. Again, it is how you look at the problem. And you're right, doing the domain, but it's where, as I said, I was explaining here, this is not clear, even though people do it, because they want to do a cross product. I would honestly write, I'm writing with a mouse now, if you can guess, cross y. I'd rather do this than this, because it's clearer to me, oh, I'm doing the cross product, I'm not, but it was, if I was writing by hand, I'd do this. And by context, it's obvious that this is the cross product. In fact, sometimes you might want the wedge product in there as well. But this is obvious what this is from the context. But this, from reading it, it wouldn't be. So you would need a little bit more. The name of it is better, even if I know my domain. Because the problem here is these do not annotate themselves. So I would actually have to write these out a bit better and say, okay, this is a vector. Okay. And then I'd do this. And then when I'd be reading from the context, I'd have to give names better. I'm like, from the context, this is actually saying this is a cross. Again, this is bad. I'm writing with a mouse, it's awful. And yeah, I've actually, Odin ages ago, I should say this, I actually experimented with infix function calls as well, for procedure calls. So I actually explained this. So I actually experimented with this concept. So you could do the, I can't remember what the syntax was. It was something like that. You could do this, and I don't remember. I think it was just like a whatever, something like that. And I found out I never used it in practice ever, like virtually never. Which was a surprise to me. I'm like, why? Of course it sounds like because it was never actually I needed it. And the other problem was I actually had the concept of packages as well. And when you're typing things, math, actually no, it's not math, it's actually under lin alg dot cross of x and y. That reads fine. Ready? Do you want to see what happens? Oh, that looks awful. I don't want suffix notation. It turned out to be an absolutely dreadful idea. I had both suffix and infix were actually identical technically at the end of the day, but it turned out an awful approach. And this, it might have looked like this actually. I don't remember what it was. But the problem was, this wasn't easier to read. This was harder to read, harder to comprehend, harder to write, and it also was just as verbose. It wasn't easier. And so in practice, I didn't want it, is what I'm saying. And that was where it went, oh. But this is the problem is you'll want to be very specific. So this is the problem is you want a very specific domain for your thing. So you want a domain specific language, which is very good idea case in some cases. This is where like GLSL or HSL or whatever, or meta language, or these shader languages, they are very specific to their domain. They have a certain set amount of types and how things work and what you can do in them, because they're for that domain. You wouldn't ever want to use GLSL for, say, I don't know, making a hash table with. In fact, I don't even think it's technically possible, because you can't do pointers effectively. Well, you can do that, but I mean, a dynamic hash table is meant. You can't really do it. And you can't do pointers in there or anything with the pointers, so you're actually kind of screwed. If you're doing pointers, you're doing offsets into arrays, so you can bypass it, but you're not doing it properly. So you can't do it. It's... different languages have different domains, and when I'm looking at the systems level stuff, it's not really dealing with mathematics. If I'm doing mathematics, I'm going to use Python, or I'm going to use Mathematica, or MATLAB, or Maple, or Julia, or whatever the new languages on the street are. And it doesn't... there's all these different things. And my issues with all these different things is kind of a weird. I'm thinking I'm going to call it a night in a few minutes, so I'm just going to turn this screen up so you can probably see it. We could always do the Ginger Bill one as well, but no, I think the Odin one looks better. But no, it is the problem when you're programming. Types have proved themselves to be useful, but it's very difficult to even know why. And people just use things and they just get used to it. And that's what I find very interesting myself. That there is kind of a way of dealing with things. And it's... what's the best way of putting it? Yeah, that's what I'm going to say, yeah. So the problem you have is that sometimes people use concepts and they don't actually understand them. And that's fine. You don't actually have to understand things on very deep levels. If you understand, like, just know how to use it, that's 99% of the time, 99.99% of the time, that's good enough. But when you actually start to actually question the things like, why do we use types? Or you have properly understanding them. That's a bit difficult. Like, why is this case? Like, I think some people have heard me say this before, but I think structured programming is the correct way to program. It is not obvious why it's the case. What I mean by structured programming, I mean scopes, I mean if statements, for statements, switch statements, like general stuff like that. Constructs where it's structured, defer statements. I do not mean non-structured structured statements like go to, like a jump statement that just jumps over and ignores the scopes and everything. So the question is, why do I say structured programming is correct? And not that, there actually are use cases for go-to and stuff like that. No. Structured programming, even though technically it would be implemented with go-to internally, you do not need to use the unstructured approach in practice unless you are going to assembly. So why do I think structured programming is correct? The simple option is, it sounds like I'm going to say a tautology, but no, it's structured, so it's easier, it's a better way of, you can actually structure your ways of thinking. It's a way of making sure all these constructs are together. In fact, that's how things are. Like, okay, a loop, you do this with part of the loop, so it's in like a body of it. So you're actually having bodies everywhere. You've got this kind of hierarchical structure of things and they show the procession of things. And it's very interesting. Like, this is just a parser here. So let's look at it here. So we have, if this condition, great, we're going to do this body. If it's not, else it's this body. And then if we've got a for loop, we've got in this body of the for loop. We've got a switch statement here, and you've got different cases with each of them getting bodies, which is what a scope is, effectively, a body. And it's kind of a nice little hierarchical structure. But the thing is, every problem can be expressed this way, which is interesting. Now, sometimes you do need to get out and jump out of these, like break out of this loop. So you don't just follow it top down, you need to break out and start here. Now, the thing about the breaking out, which is interesting, is that, what was I saying? Yeah. When you break out, oh, you can't see what I'm talking about, it doesn't matter. I know, it's hard to tell because I'm looking at one screen and then there's a preview, it doesn't matter. But when you're breaking out of a code, it is still structured because it's with reference to its parent. It's not just jumping to a different line in the code or a different aspect. So a break is still in that case. So it's still structured because it's with reference to the structure of the program. So it sounds like a bit of a tautology, but it isn't. That structure programming, it allows for structure because it has semantic information about the rest of the program. Go-tos themselves aren't really semantics. They have minor semantics in the fact they have blocks that are named, but they're more shorthand than actual structured in the actual data. Sorry, that's a big woof there, but yeah. But some things like that are not obvious for most people. Because why are they? It's not obvious to me. It took me a long while to figure that out. It's really fun, and that's also the thing, is like there's loads of stuff to figure out in like programming still. Like I honestly would say the what is it, you could say the epistemology and ontology of programming is kind of a very, very unexplored area. Yes, there's loads of the theory behind like type systems and all that lot, but there's not really the theory behind anything else. Do you think there are cases where go-to should be found? Go still has a go-to, and I found use cases for it. I'm going to state no and a no. The argument when you should be found is when you actually really need to write assembly code and you really need to have like proper like jumping around all the time. By then you shouldn't be using a high level language like C. Effectively is a high level language, but Odin is a high level language as well. You're effectively wanting a low level language. It's a different problem. But for a high level language, you don't need it if you've got all the proper structured constructs as well properly. But go-to, yeah, Go has go-to, and yes, there are use cases for it. But you can mimic go-to in many different cases, and you can mimic it with different things while keeping it structured in nature. So one good case that go-to has, that many people using go-to, is to when you're in a loop, you go back to the beginning of a function and call itself again. So you're effectively, in some cases, you're kind of mimicking tail recursion. That's one way of thinking about it. Or another way is you're you're mimicking tail recursion is effectively what you're doing. But many languages know how to do tail recursion. Go doesn't. It actually doesn't know how. It doesn't do tail recursion optimization. But that's effectively what you want. So your loop, the thing that you going back to think is you could turn that into a sub procedure, like we could do a nested procedure in Odin, and you've gone back to it. I'm going to actually find use cases of go to use cases, because I can't think of many. Another use case of go-to is when you're in a big nested thing and you want to go to a general use case. Well, for me, I split them into literal sub-functions and call them. So, oh wait, I've got tail recursion again. It's something like that. It's effectively what you're doing. It's the same as what go-to does, but it's structured. The go-to thing is more of a, hey, this is how I do it in assembly, so it's fine. But yeah, that's another way I was just thinking. But that's effectively, that's what I'm just thinking, that is what you're doing. You're just trying to, yeah. I can't think of another, I'm going to make the hypothesis statement. There is no case for go-to which cannot be replicated with a structured alternative. I'm going to state that. There is not a use case for unstructured stuff where you cannot use. So, right, I'm going to state here, you're saying you're using like threaded interpreter and you're using go-to like labels as variables, like in, you can use labels as variables in like GNU-C. So that is a good use case, but effectively I wouldn't use that in C, I'd just write that in assembly. That is an assembly thing in my opinion. And you can actually do that still in a high-level language, because that's how like Go works with its coroutines everywhere. like you state things, or whatever. It adds all the stuff in there. So it's more of a, again, I'm trying to make the example of a hypothetical structured language that did everything. You can. There is no theoretical use case where an unstructured case is better than a structured case. You could literally do it every single time. For a high-level language, I should state. Not for the implementation, because clearly implementation's in unstructured. Because the structured things are made from unstructured concepts. That's kind of how it builds on. That's kind of a hypothesis. Is it a hypothesis or is it conjecture? No, it's a conjecture. Technically, it's a conjecture. Because I bet there could be a proof. Any more questions before I go to bed? Did I actually answer all the questions this night's stream? I missed one or two, I know. Oh, well, one question, sorry, was Tetralux. Random question. Did you glance at... Did you glance at the assembly you posted? And do you have any ideas why it might cause? As a reminder, it doesn't work. You only have this a problem on the unoptimized code. Everything else works when it's optimized. What? All I can say is I can blame that on LLVM. Seriously. Because if it's working on like opt 2 and opt 1, but it doesn't opt on opt 0, yeah, there's something else going wrong there. Something is like, that's a bug. Code generation bug. I don't know if it's on my side or LLVM's side. It's usually LLVM, but I don't know if it always is. Yeah, sorry. Again, some of the people in completely of the chat were talking to me. But yeah, again, it's something I was explaining Spherical Harmonics earlier. It's one of those, me explaining it in an hour is not going to help. You're probably... it's probably one of those things I would probably have to make a big course on, because it's one of those, even like complex numbers, you can explain them in an hour, doesn't mean people understand them. It's because, again, my thing is, if I was going to explain quaternions, the way I always explain quaternions is from a group theory perspective as well. Like if I was doing a lecture series on quaternions, the way I explain them is from a group theory perspective, like saying, okay, here's your complex numbers. Here's the complex numbers as rotation. You can use the complex numbers as rotations. And look, you can express the rotations as a 2x2 matrix. They are, all the rotational matrices are 2x2 matrices with real components. Done. And the same with rotations in 3D. You can have a 3x3 matrix and you do the same thing. But you can also express them in a slightly different way. You can use 4x4 matrices as well, or 2x2, 2x complex matrices. In fact, the matrices you're wanting to do are called the SO3 matrices. The SO2, you see what I mean? But you're explaining it through this, which these sounds like really more complicated. But once you realize, actually, no, they're even, it's a simpler way of looking at the thing. And then you understand what quaternions are actually doing and what they're representing. They're not just these 4 random numbers that do magical things when you multiply them together. No, they represent this particular set of operations which are related to the rotations in 3D space. It's all this maths. There's loads of maths everywhere when people is like, what are you doing? It's like, yeah. And it's sometimes I am just explaining. I don't like the way people explain quaternions. Like, especially I'm talking like computer graphics. They're talking. This is where it's like Spherical Harmonics, computer graphics earlier, because the way they teach them is confusing, in my opinion, in the fact that people usually don't know complex numbers that well before, and if they do, they probably only touch them slightly, and then you're talking about higher level dimensions and like, oh, they're non-commutative and the elements are anti-commutative. It's like, what the fuck are you talking about? But when you actually like, no matrices, yeah, okay, so we can start from matrices and start building up from there. And it's okay, you can show the symmetries between them, and there's an isomorphism here, and there's a homomorphism here, and you have to learn what those terms mean. And once you've learnt from that way, you realise, oh, quaternions, oh, they're nothing then. Oh, that's easy enough. Okay. And it's like, okay, so the quaternions don't become the complicated thing anymore. They just become the thing that pops out. So there's many things. I might actually just do math series. I might actually just start doing that. Like I said, I was going to do a... yeah, like I might actually just do a math series, especially along this podcast series, because I'm thinking there's a lot of maths that people seem to be teaching, and it's like, that's wrong, or that's dodgy, or that's not a good way of explaining it to people who don't know the topic already, like they haven't got a maths or physics background. Like they may be explaining, it's like, I'm trying to think, what are maths topics? Like, what math topics do you that are like in programming a lot that people are confused about? Or just give me a list. Seriously, I'll probably do it. Just tweet me on like the Gingerbill, or email me at like what's my email address? Bill at odinlang.org. That's one email address. Or Bill at gingerbill.org. That's another email address. Whatever you want to do. Just send me more questions about that, because I won't do it in the email. I just want to do the series, of course. Because where the like discrete cosine transformations are good. Okay, so that was related to what we did earlier. So discrete cosine transformations are another way of expressing, they're called orthogonal functions, and it's a different way of decomposing things. So there's one-dimensional ones and two-dimensional ones for discrete cosine transformations. They are effectively the same as Fourier transforms, and I'm going to save them for a series, but the same as Spherical Harmonics. They're just another set of orthogonal or orthonormal basis functions that you can use. That's all that they are. Okay? That's all that they are. You also have... They are pretty much identical. There's also like maths for matrices and stuff I would do. That's also pretty good as well. Like 2D and 3D stuff is always good. 2D maths, you can get away with a hell of a lot of not knowing anything. You can just get basic triggers, probably all you need. 3D, you need a little bit more, but not much to do the basics, of course. So maths is one of those things that keeps going further down and further down and further down. It's totals all the way down. But yeah, that's short. So there's many things. If you've got any more topics, please tell me. Provide pseudocode, yeah. If it's just theory, people will not be interested, yeah. But the problem is, you need the theory and the pseudocode at the exact same time, because otherwise you don't understand what's going on. What I mean by that is, just let me get a glass of water, mate. Water, good. It's good for you. Is that, as I was trying to explain the stuff, is that to understand what you're doing, you can show the code and it's like, it doesn't have any meaning to me. It's just numbers. It's random crap. You need to understand the theory, and you need these visual diagrams usually going on and stuff. And then you can show how you would implement this in the code. So I'd have to plan the series out, but there would have to be many things. Some of them I might just sell as well, like little series charging. They won't be expensive, like very expensive, but just something like, hey, this is what you can do. Just buy it for like a $5 or something, and then done. It just costs the covering of me just doing it for like, it takes the time and stuff, even if it's just electricity costs. But it is some of those. There is some really bad resources out there. And I'm not saying I'm a better teacher out there or anything like that. It's just like, yeah. It's something, well, he's saying it's some good or something. I've had to give Odin for free because you can't sell it. It's one of those things. Certain things you can't sell, certain things you can definitely sell. Lectures on learning mathematics for programming, definitely, you can definitely sell that. You can sell code editors. Yeah, because if code editors include the compiler, the IDE, the debug, you can sell all that packaged together. Because you can sell an IDE technically, you can sell a debugger, you can sell everything else. But you cannot sell text editor. Well, yeah, actually, it's a lie. You can. Sublime Text is great, and I bought that. It's one of those things where you can't really sell languages very well. There are exceptions, of course, to the rules. Again, these are all prima facie rules. They're not fucking ultima facie. There's always going to be exceptions, but it's like morality. There's always exceptions, even if it's objective. Welcome to reality. It's confusing. It wouldn't be fun if it wasn't. Yes, we've done the stream for 2.5 hours now. I should probably go to sleep. But yeah, there's so many aspects of maths. Math that's like, what? Yeah, loads. So yeah, I probably should go to sleep now anyway. So thank you all for watching. If you've got any, seriously, if you send me some emails, probably like math@gingerbill.org, and give me some questions, I could probably do some series on this because it's actually a really good idea. So please tell me some good ideas. I could probably teach you if you've got any questions, especially programming related stuff, because I'm trying to target this for programmers who want to get better understand the theory and the applications of the stuff behind it. Like, it could be like, what are complex numbers and why are they useful? Or like, again, the quaternions and stuff. Another stuff would be, the other thing is, like, again, was spherical harmonics or discrete cosine transformations, or how are everything of these all related together? How about a Fourier transform or a fast Fourier transform or stuff like that? And stuff like that, what is the mathematics behind it all? Yeah, I can give it a go. So, thank you all for watching. And actually, I've got an idea for that. Don't worry about that. So, thank you all for watching, and good night. It is now Thursday. So, good night.